in our IEEE webinar. So, like a brief introduction to Sir. So, Dilip Sir serves as a Vice President of New Technology Research and Development at Reliance Geo Platforms Limited. He is also presently a fellow at the Center for the Fourth Industrial Revolution at the World Economic Forum. He has a PhD in electrical engineering from the University of Illinois at Urbana-Champaign. He has worked at Intel, Qualcomm Research, and IBM Research, and has taught at UC Davis. He is an inventor of 60 plus granted US patents and has authored 70 plus publications. He is a BTech in Electronics and Communication Engineering alumnus of IIT Madras. So, sir, it's a great pleasure for us to invite you, and thank you for giving us some time from your busy schedule. Even now, all the participants are joining, so it's my request to all the participants that please keep your microphone and camera off during the session. If you have any doubts or questions, you just can write the same in the chat box. All your doubts will be answered at the end of the session. And in between, please do not turn your mic off unnecessarily unless if some very emergency is there. After the session, when the question and answer round will be there, so there you can unmute yourself and discuss whatever we have with Sir. So now we are about to start our session. So please be attentive, and thank you all for your patience. Sir, welcome, and you may now share your screen and start the session. Thank you, sir.
Thanks, Devoshi. Still get the yeah, happy to be here. And actually, my PhD thesis advisor at Illinois was an alumnus of IIT Kharagpur. Perhaps you might have heard of him, Prit Banerjee. So I'm more closely connected to the campus. So anyway, I wanted to cover some aspects of quantum computation, but also wanted to give some physics-related introduction as well. So if anybody's getting started in this, I myself am getting started in this. So things that I have understood, I'm trying to tell you here. But it's sort of good to get the flavor of what's really happening, maybe with these photons and stuff like that, while we actually do the processing. Because sometimes we may just get involved in the computation and the matrix algebra and things like that, and but you might lose track of what happened with the physics there. So it's good to have some background, so I thought I'll talk about it. Also, Deboshi wanted me to talk about what in general is happening at in research and things like that. So I thought I'll have some introductory slides on 5G and microservices and where we're headed with programmable infrastructure, and then we'll dive into the quantum talk. So what we see happening with 5G data networks is that we'll have the infrastructure completely virtualized. There can be cloud data centers, in-network data centers, edge data centers. These functions will be placed in these different data centers depending on the resource availability, the latency required to provide service, and so on. So there will be a distributed SDN frame control plane on the left that will control all of this. Some of you are working on the communication layers, and this thing extends all the way down to the remote units, distributed units, central units, and so on for wireless processing. And while things may be processed wirelessly, at some point you'll have packets, and then it all becomes software at that point. And then now we are also looking at how to uh, have a very modular implementation, so that, let's say you come up with an algorithm today for optimization. Tomorrow you want to switch it to something else. Then it should be easy to kind of switch from one microservice to another, and so on. Even as standards evolve, you can just start a virtual network function for a new standard and so on, and turn off the old one. And it's not just network functions, any services, applications, all of them can be implemented. And typically the framework is microservices based. And you have to look at latency constraints, user mobility, resource availability, security, and think of something that does this. And then you are coming up with, doing your research and coming up with some algorithm, whether it's for AI, machine learning, or whether it's some quantum-inspired algorithm or some blockchain algorithm. So those things you can plug in. Also, edge computing is huge, and we'll have all kinds of services and applications deployed at the edge. You can think of, even if communities are not connected to the rest of the world, they could be locally connected. You could have a local WhatsApp or Twitter or Facebook, email, and so on. You can have local Wikipedia, ebooks, newspapers. You could cache news and video in local languages. You can have local healthcare, banking, and you can have local drones now also delivering things, especially when people cannot get out. So, with COVID and things like that. So, technology can help. And also can have different kinds of connectivity stacks as well, and you use the best possible stack. And like I said, most of these things are getting implemented in a microservices-based framework. So there's this trend towards disaggregation, and so that you can scalably replicate these microservices dynamically. And so, let's say you're taking care of mobility. During the day, a lot of people are mobile, and microservice related to mobility may have more instances in the programmable infrastructure. And as you go down into the night and everybody goes back home, you don't need that many instances. So dynamically, you can scale each microservice, right? But at night, maybe you're watching more video. So you want a virtual content delivery network microservice may scale up and things like that. So these are the kinds of things. And then as you think of these microservices, think of you as a person being an expert in some particular area, and then you're developing a microservice, whether it's for some machine learning application in wireless networking, or some quantum-inspired algorithm, some blockchain system, and so on. So actually, this system that we have implemented has been nominated for an enterprise award in Toronto. We'll see. Right now, it's just one of 4 teams. But anyway, I think we're doing good stuff right now in Geo. So, and essentially, you can think of all of these things, technologies coming together: 5G, IoT, AI, blockchain. And all systems can monitor, provide triggers. Smart contracts can execute some intelligent logic. Blockchain platforms can provide trusted storage, recording, and in all, you would have this distributed smart network doing cool stuff. And in the future, if there are complex algorithms, maybe we might have quantum-inspired microservices and algorithms to solve, an optimization problem. Some examples for healthcare, for example, a patient is having a wearable and it's connected to an IoT service, connected to a 5G network. Something happens, the patient is not well, the system detects it, The patient is driven to the nearest hospital. And during the drive, a blockchain network can come in and transfer the data, the patient data, which may reside in a primary hospital, to the nearest emergency hospital in the background. And on the blockchain, you record the fact that the event happened. So it's more of a control plane on the blockchain that's giving a trusted record of what happened. Because patient data is private, you won't record it on the blockchain, which is an immutable ledger, which means it cannot be changed, but you record the hash of the change form. And then the patient can, you can even authorize insurance and automate, process that, and, as soon as with all the information and all that, the patient can receive emergency care and potentially may even use drones to deliver medicines to the emergency vehicle if something is needed. So, and you could be doing some dynamic optimization with the quantum algorithm to optimize the flow path. So, also, similarly, smart energy and transportation are becoming big. How do you manage microgrids along with the traditional grids, and with electrical vehicles and things like that? They are, from the transportation side, they're actually putting a demand on the grid. So that, how do you manage all of this and things like that? So these are all interesting problems. So I just wanted to give some intro, and I will switch to quantum. And if anybody has any questions, this was just a general intro. If anybody has any questions, let me know, or we can. Okay. Yeah.
No, sir. You can proceed. There is no question yet in the chat box.
Okay, sounds good.
I will let you know whenever I get any questions in the chat box.
Okay, sounds good. Okay, so I'm not sure how many of you studied the Young's double slit experiment in high school. You probably did, and you're familiar with photons coming in, hitting two slits, and an interference pattern forming at the back with the constructive and destructive interference. And the thing is, for a long time, it was thought, hey, these photons are coming in, or electrons are coming in, and it's actually a whole bunch of them coming in, and some take one path, some take another path, and these waves interfere, and that's why this pattern is caused. But a real interesting thing that was done is that even if you slow it down to just a single photon going to this double slit, nothing else, you actually, it actually goes and hits different parts of the screen and causes, you put a single photon at a time, and then you observe this over a period of time, and you get this interference pattern. It's as if this collection of photons spread over time knew that they had to produce this interference pattern. It's just remarkable how that happens. So, is it a wave? Is it a particle? So it has been observed even with molecules. Like Buckminster fullerene kind of molecules with carbon atoms and things like that. So even large molecules have shown this behavior. It's very interesting. And how do you interpret this? It's neither a wave nor a particle and things like that, but it has some characteristics. And so what quantum physics tries to do is come up with a framework to describe this behavior. I mean, we are at a macro scale, we're used to thinking in terms of waves or particles, but there is an inherent behavior that we have to describe, and that's what the mathematics tries to do. And the presumption is that every particle is in a superposition of states, and the measurement on the screen collapses the state to one of the possible states. So, for example, in this case, which path did it take? So, just going over some physics, like E equals h nu, right, or hf. This is Planck's constant, and h bar is a reduced Planck's constant for h by 2 pi. It becomes useful when you think in terms of angular frequency, like the equal. So omega is 2 pi f. Then if you want E equals h bar omega, then you would say it's the same as hf, right? So h divided by 2 pi into 2 pi f, and you write h bar omega. So, and you might be familiar with de Broglie's equation for matter waves. Lambda, the wavelength, is h divided by p. That also, if you do the 2 pi thing, h divided by 2 pi, and multiply with 2 pi, then you can write p is h cross k, where k is 2 pi over lambda. So just shift p from here to here, lambda comes down, and then this is h divided by 2 pi, and then 2 pi by lambda is k. So this is called a wave number. It's related to the wavelength. So, and then, if you have a particle, you can have a kinetic energy. You can write it as p square over, if p is mv, you can write it as p square over 2m. Now, is this, so, velocity is wavelength times the frequency, right? That's the same thing that's been written here. So if you have 2 pi f, that is, and then k is 2 pi by lambda, if you take the speed is f times lambda, that can be written as omega divided by k, right? Because k is 2 pi by lambda, so the lambda comes on top, and it's 2 pi f. So this is normal definition of speed, right? But then let's multiply h bar the numerator denominator, but h bar omega is e, and h bar k is p. So then speed is energy divided by momentum. But then, hey, if it's half mv square, and then mv, dividing the two, you get v by 2. So how can speed be half the speed? So it's like this paradox, right? So actually what's happening is that there's something called a group velocity. This is a bunch of waves in superposition, and they have a velocity in a group. And essentially, this omega is a function of k, and it's slightly varying. And think of it more like this function, more like a very sharp Gaussian. It'll peak at some point, and around that it will fall off. So this is how they interpret it as a group velocity. When you do that, when you're actually taking d of omega by dk is dh bar omega by dh bar k. You multiply both numerator and denominator of h bar, and then this is e and this is p, right? And so it's d by dp, but e is half mv square, p square by 2m. If you write that, then derivative with respect to p, now the 2's cancel out, because you get a 2p and there's a 2 at the bottom. You get p divided by m, and v by v. So the interpretation of this packet as being a superposition of waves with a group velocity is what comes across. And then, so for that, once they realized that this is what was happening, they defined what is called a wave function for a particle, which basically now, you've seen this kind of equation, right? Like an equation for a wave train and stuff, like e raised to I kx minus omega t. Now this thing, what's happening is k is changing the wave number, and omega is changing as a function of k. But this essentially doing integration is a superposition of a few waves centered around that peak of the Gaussian. And this is the amplitude of those waves. And so think of this whole equation as being a superposition of waves representing a group of waves that's moving along the packet. So, and that whole thing is called the wave function. So, familiar with the Taylor series, for example, let's say omega of k. I was saying, right, this omega of k is like a sharp Gaussian. So let's say it peaks around, the mean is like k naught. You can write a Taylor series expansion around it. So W of k is W of k naught plus k minus k naught, first derivative at k naught plus remaining terms. So let's say this remaining terms are negligible. Now this is what we defined, right, as the group velocity, the rate of change of omega through k. So if you write that, this W of k, first order approximation becomes this. The remaining terms are negligible. If you plug that into the equation, this W of k naught is a constant, k naught Vg is a constant. When you plug those things into this psi of xt, like kx minus omega t, substituting W with the expansion, those constant terms we can pull out, right? And so they're coming out here, you can see them. And then you're left with kx minus kvgt, or ik into x minus vgt. And if you look at the amplitude of this, which is taking this times its complex conjugate, then these terms are just phase and they disappear. And you're left with square of this integral. And now if you look at this thing, it looks like, hey, what you have as a function of x and t, if something is peaking, at x of t, it's as if it is shifted by x. If you have, at time 0, if you had a peak, then that will show up shifted in time with vgt. So it's as if this whole thing is moving at the speed of vgt. From what we can see with this kind of this group interpretation, so group velocity interpretation. So that so these wave functions satisfy system that you want to minimize, that is h. So it's a real number, but now you have I is an imaginary here. H bar is just a constant. So I times d psi by dt should be h psi. Like this guy is real. So for this to actually if psi was real, then d psi by dt would be real. Psi here, this would whole row of right hand side would be real, but there's I. So you cannot have psi as a real function. So the solution for this equation is a complex function. But in reality, we measure and it's the probabilities that we're concerned about in the quantum processing. And they relate, will explain like it relates to the energy square of the wave function. It's modulus of the square. So essentially you take psi and psi conjugate product, and that's what you typically are interested in quantum processing. So now again, coming back to this equation, we just said this is the equation governing the system. That is, take the time derivative, multiply by IH crossing, that should be the energy times the wave function. So is that valid in this case? Well, so if you differentiate with respect to time, all of this is a function of k, so you get minus IW coming out, multiplied by IH bar, and so then you get minus IH squared H bar, and then the rest of the integral remains the same. So minus I squared is 1, and this is just H bar omega, or HF, right, which is the energy. So that's why if you have this, then it satisfies this equation. you take IH bar d psi by dt, you get the energy times wave function. And you might have also seen, like Schrodinger's equation and stuff that also, this was a time derivative earlier. If you take the derivative with respect to x, second derivative, if you differentiate this with respect to x, you get this ik twice. So you get I square k square, which is minus k square psi. And then if you multiply that by h squared by minus h squared by 2m, you get h squared k squared by 2m, which is p squared by 2m, which is the energy, which is E psi, which we know is, which we just saw is IH bar d psi by dt, right? In here, we saw that IH bar d psi by dt is E psi. So now when we try to look at this, it turns out to be this, which we saw was this. So this is actually a free particle Schrodinger equation that you were solving. So this is kind of the equations that these quantum particles will obey. You might have seen real wave equations like dtu by dt square is c squared dtu by dx square. So in quantum, there is like a single time derivative instead of a double time derivative. But the size are complex, right? Now, it turns out these kind of functions, yeah.
Sir, actually, sir, we have few questions. So, like, will you address them now, or like we will take it?
Cool. Yeah.
So, sir, Mr. Anirban is asking that how will you store the enormous data that would be generated in every nanosecond by a quantum computer?
Okay.
So that was one question, and another question is like, has anything been done to investigate why the phenomenon of collapsing states upon measurements happen? By Mr. Shamrat Mukhopadhyay.
Okay, so typically what you do is, to answer the first question is, you actually do not bother a quantum computer. You give it some inputs and you let it run. The thing is, and we'll come to it in a bit, but basically, the state of a quantum particle in a quantum computer is in a superposition of states. That's a private state associated with the particle. You cannot touch it. So you have, it may have some probabilities associated with those states, but you don't know what they are. The moment you try, and now this comes to the second part, which is collapsing. The moment you try to observe that particle, it will collapse to one of the states. And after it collapses, it forgets whatever it was in, whatever superposition state it was in. It will only remember now, you collapsed me to the state, I'm in this state. So if it had a superposition of spin up and spin down, and now it collapses to spin down, it will spin down. Right? So, but before you observed it, and you probably heard of the Schrodinger's cat paradox, right? So there's a cat and in a box, and there's if some radioactive particle is emitted, some poison may be released which would kill the cat, but we don't know whether the radioactive particle was emitted or not, which would have caused the poison to be released. So when you look outside the box, you don't know whether the cat is dead or alive. But when you open the box, you will see that the cat is either dead or alive. So the moment you open the box, the state of the cat has collapsed, and that's where people have, the classical physicists were tormented about this. But it's not that the cat died and then when you open the box, you just saw it if it was dead. It just so happens that when you try to observe at that point, the quantum particle actually collapses to other states. When you try to observe, then you collapse. So that's just the nature of it, and really, and the fact that you cannot the superposition state of the particle is private to the particle. It prevents you from even capturing any data associated with it inside the quantum computer. So, and it's only when you observe it, you get the state of all the qubits, and you say, okay, that's what the quantum computer gave me, but you don't know what was happening inside. So you don't have to worry about all of that data because you have no access to it. I hope that answers the question. I mean, it'll get clearer as we go along. So as I was talking about superposition, you may have, a photon could be spin up or spin down, or an electron could be at different orbital levels going around an atom. These are all possible states for the electron, or different possible states for the photon. So conceptually, you just talk about it as a state 0 and a state 1, and this is called the Ket notation. And you say this 0 is one state, and this 1 is another state, with this vertical line and the state variable, and then a greater than sign next to it. So then you say that the quantum particle is in a superposition of these two states. Like this could be spin up, and this could be spin down. This alpha 1 and alpha 2 are amplitudes associated with these states. And the probabilities are the squares of this if they are real, or it's the product of the complex conjugate with, so alpha 1 conjugate times alpha 1 and alpha 2 conjugate times alpha 2, such that the probabilities add up to 1. And I'll give you an interpretation soon as to what these probabilities mean, these amplitudes are, just a bit. So, but this is the typical representation of a qubit. Okay. So this is the wave function, the psi of x of t kind of thing. Now it's like simplified and just written like this. So you don't have to worry about what's really happening as a function of time, or where the electron is going around the atom, or whatever. So you just write it in this form. So now what happens is when you have a beam of light, let's say, moving, essentially the electric and magnetic fields are perpendicular to each other, and they are oscillating back and forth, perpendicular to the direction of propagation, right? Now, the electric and magnetic field are perpendicular to each other. The direction of the electric field is called the polarization. Okay. Now, if the wave is propagating in a particular direction, the electric field could be in any direction all along the 360 degrees in the plane perpendicular, right? And whatever that direction is, that's the polarization. And perpendicular to it is the magnetic field H, such that, there's a pointing vector, which is the direction of propagation for the electromagnetic wave, which is E cross H. So main thing to remember is the direction of the electric field is a polarization. Now, we have a polarizer, right, that selectively lets something through. If the polarizer is polarized completely perpendicular to the direction of the electric field, nothing goes through. But let's say the electric field is at an angle theta with respect to the direction that the polarizer is letting information through. Then what happens is, if the original amplitude is A, then A cos theta is what gets through the polarizer. Now, A is the amplitude of the electric field, and A cos theta is getting through, is amplitude that's getting through. The energy is proportional to the square of this. So it's proportional to cos square theta, right? And so cos square theta is the fraction of energy that gets transmitted past the polarizer. Now, if you have a bunch of photons and all in different directions, then there's a probability of cos square theta for the photons to go through depending on the polarization at the end of the polarizer. So think of this cos square theta as probability, and this probability relates to the energy. Okay? So that's where when we see this kind of equation, right? We see these amplitudes. This is like the e cos theta, e sin theta kind of thing. But the probabilities of the squares, because that's and they reflect the energy of the amount of fraction of energy that went past. Now, so if you describe this photon coming in at an angle alpha to the polarizer, then the polarizer is only allowing X through and not allowing Y through. Then you can say cos alpha and this state along X, and then sin alpha photon symmetry Y. But this is going to get filtered out. So beyond the polarizer, the state is just photon X, right? But and now that amplitude is 1 because there's nothing else that is there. But before it went through, it had the probability of cos square alpha to go through and sin square alpha to not go through. Once some fraction of whichever fraction of photons went through, they are all in this particular state. They've collapsed to this state. All the ones that are moving along the X direction, they're all collapsed in. So you can think of measurement or collapse in this manner, right? But after measurement, there's only one state. Right? Before that, it was in a superposition of states with these probabilities where the square of sum of the squares, cos square alpha plus sin square alpha equals 1. And there could be multiple states, more than just 2, in general. But all those squares of those probabilities, all the squares of those amplitudes, all add up to 1. So this is what we were just discussing a little while ago. The state of this quantum particle is not accessible to us as such. I mean, if you just want to know, hey, what is this current amplitude for each of these 2 states that is in, you actually, if inside a computer, quantum computer, you actually don't know what it is. If you try to observe it, will collapse. But you can manipulate it by, doing some quantum processing, putting it through some quantum gates and things like that. But you make it stay inside that domain. The moment you take a measurement, it comes out as a classical state. So, the moment you observe the state of the quantum particle collapse and any prior information is lost, and the state after measurement is a collapse state. Now, there's also this thing called no cloning theorem, which also says you cannot clone a particle, and this kind of follows from the fact that you cannot figure out what is the superposition for you to create a clone. You know what the possible states are, but you may not know what the probabilities are. But what happens inside a quantum computer is that you try to manipulate with the state such that if you're trying to minimize the energy, keep taking the system, you keep doing some calculations, trying to minimize the energy, such that the lowest energy state has the highest probability. So if you take a measurement, more likely than not, you get that as the answer. So that's what we try to do with quantum computing. So typically 0, you can write it as a column basis vector, 1, 0, and 1 can be represented as 0, 1. So now the superposition of states alpha 1, 0 plus alpha 2, 1 can be written as alpha 1, 1, 0 plus alpha 2, 0, 1. Or, if you add it up, you can write it this way also. But you try to write it in terms of this basis. Now, if the states are equiprobable, then because the squares of these are the probabilities, alpha 1 square should be half and alpha 2 square should be half. So alpha 1 is 1 over root 2 and alpha 2 is 1 over root 2. But it could be plus or minus, it could even be complex, it could be e raised to j theta by root 2, things like that. So, which is just a phase shift or a rotation to the direction. So that's one qubit. Now you could have another qubit, psi b. What are we doing on time? Okay. So that also can be written as a superposition of states, beta 1 0 plus beta 2 1. So where the sum of probabilities are 1. But the combined state of the two particles is written this way as a tensor of Kronecker product, which is psi a, which is alpha 1 0 plus alpha 2 1. Tensor product of beta 1 0 plus beta 2 1. And then you cross multiply each one of them, you get alpha 1 beta 1 0 product 0, alpha 1 beta 2 0 product 1, alpha 2 beta 1 1 product 0, and alpha 2 beta 2 1 product 1. Now, what is the interpretation of this? I mean, we'll come to that in a second.
Yes,
but, yeah.
Yes, sir, we have a few more questions.
Mr.
Mridul Gupta is asking that how does state quantum particle affect the development of algorithm or particularly conversion of already available algorithms?
So actually, some interesting things are happening. There was a research paper that was done for recommendation systems, right? I mean, but what they tried to do was write the algorithm even classically, but as if it's a quantum state. So it's a superposition of many different things that you're trying to explore at the same time. So by trying to just even classically, if you try to think differently that, hey, there are all these possible states and I can do some manipulations on them simultaneously, then maybe I can do some quantum-like computations on them such that the probabilities change, and then you can find out which state is more probable and so on. So, there's a document from the National Academy of Sciences that is showcasing this work, and it's basically saying, hey, you don't have to wait for quantum computers. We can even think of quantum-inspired algorithms as well. Just think in this manner that you're thinking about all possibilities at the same time and try to modify all these probabilities at the same time, and you might come up with a different data structure, because your data structure has to be such that it actually represents all possibilities at the same time, and then you manipulate it, right? So that makes it different from the way a normal algorithm would have written, which would have been, hey, let me take say an initial set of values, make some change, see what happens, make some other change, see what happens. But in a quantum way of thinking, you have all possible values being explored concurrently. You make changes to all of them concurrently and so on. So it might actually create a paradigm shift in how algorithms actually get developed. So it can be interesting.
Sir, another question is will the photon get split into two parts in the polarizer?
No, it doesn't. So it's a full photon that goes through. Even in the double slit experiment, it's not like one part goes here, one part goes there, things like that. It's a complete photon. Either it goes through or it doesn't go through. It has a probability of going through.
Okay. So is there any chances of multi-state transition for the photons?
Now, what does that mean?
In which, the states, the entire photon is traveling. So from which state to which state? So that's.
Can you repeat the question again? Multi-state?
Multi-state transition of the photons.
Oh yeah. So you can generalize this to multiple states, but you will represent this typically using more qubits. So let's say you had 3 qubits, then that represents like 8 states. So yeah, you can have multiple states and superposition of those states, things like that.
Okay. And sir, another question is like, sir, related to that, sir, how like this much of Mr. Anirban is again asking that, like how, like, do you have to learn all this quantum physics in order to learn quantum computing? So how, sir, this will help in quantum computing? So that he wants to know.
Yeah, I think at least you should learn some of the basics, which is I've presented. But yeah, probably as long as you know, have some rudimentary understanding of what might be happening. Afterwards, you're just working with these ones and zeros and maybe thinking quantum as if you're exploring multiple things at the same time, right? Just think in that manner and try to come up with an algorithm without worrying about quantum, you know. But I'll show some examples and some screenshots from some simulations and stuff. So
Yeah. Okay. Thank you, sir.
yeah. But the goal was actually to try to introduce these things to you so that when you see it, you don't get scared. So let me walk you through some calculation here. So and this zero product zero is written as 0, 0, simplified, and zero cross 1 is written as 0, 1, 1. Product 0 is 1, 0, and 1 product 1 is 1, 1. So what did we had this thing, right? So but now if you have the simplified notations, you'll have 0, 0, 0, 1, 1, 0, 1. So that's what we're showing here. Alpha 1, beta 1, 0, 0, alpha 1, beta 2, 0, 1, alpha 2, beta 1, 1, 0, alpha 2, beta 2, 1. Now you can verify, square all these probabilities and add up all of them up. We get alpha 1 square times this, beta 1 square plus beta square plus alpha 2 square times this. So the sum of all of these probabilities is equal to 1, right? So what's happening with these tensor products? How do you compute them? So we said 0 is 1, 0, right? A column vector. 1 is 0, 1. Now 0 product 0 is, you take, let's actually take 1 product 0. So 1 is 0, 1, right? That is here. This is 1. And then each one of those entries in 1, the 0 and 1, multiply it with the column vector for 0, which is 1, 0. So you get 0 times 1, 0, and then 1 times 1, 0. And then this gives you 0, 0, and this gives you 1, 0. So you get 0, 0, 1, 0. That is 1 product 0. And 1 product 1 is, sorry. One product 1 would be 0 times 0, 1, and 1 times 0, 1, and you get 0, 0, 0. And then if you take 0 times 0, you get 1, 0 acting on 1, 0 itself. You get 1, 0 and 0, 0. And then 1, 0, 0 acting on 1 is 1 acting on 0, 1, and 0 acting on 0, 0, 1. Yes. So what happened here? Essentially, you had a basis like this. You have an extended basis like this: 1, 1, 1, 0, 0, 1, 0, 0, and then 0, 1, 0, 0, and then 0, 0, 1, 0, and 0, 0, 0. So effectively, all that happened is you went into a higher dimensional space. From when you had 2 qubits, now you've gone to a 4-dimensional space. How many do you think you'll have when you go to 3 qubits? What would those products look like, you think, if you have 3 qubits? If you have 3 qubits, what would happen? This guy is the 2 qubit now, and you have to apply a single qubit on top of that, right? So you'll have 1 acting on this and 0 acting on this. So instead of stacking up 2 and 2, you'll have a 4 here and a 4 here. So you'll have a column of 8. So you have 1 followed by 7 zeros, and then 0, 1, 0, followed by 6 zeros, and so on. So you have all 8 possibilities. right? So, and that's how you kind of think about these types of products. But, so you have multiple qubits, you can have higher dimensional states, and those, you were talking about multi-state transitions, those become possible to represent. So effectively, 0, 0 is this, 0, 1 is this, 1, 0 is this, 1, 1 is this, right? And in general, you can have a superposition of many states, and if, say, m states and m is a power of 2, m is 2 raised to k, then you need k qubits. And the sum of all of these squares of these probabilities should be 1. Now, there are things that you could do. Now you're seeing that these states and all are just some vectors, right? You can apply some matrices on them. But typically, the kind of matrices you apply are called unitary matrices. They have this probability that you conjugate you equals you conjugate this identity. So take this Hadamard gate, for example. It's an interesting gate, but it's real, and all its entries are real, so its conjugate is the same, h plus is h. So h plus h is just h times h, the product of the h itself. So 1 over root 2 this thing plus 1 over times 1 over root 2 this thing. So you get half this matrix times this matrix. And when you multiply this out, you get 2, 0, 0, 2, right? 2, and then this is 0, and then this is 0, and then this is 2. So this is 1 into 1 plus minus 1 into minus 1, you get a 2, right, for this guy. But there's a half in front because of the 2 root 2's. And so those cancel out, and you get 1 little 0, 1, and that's the identity. So you can see that this is unitary. But what does it do? What does it do if you apply it to 0? We said 0 is 1, 0. When you apply it to 1, 0, you get a 1 here, and you get another 1, and you get 1 over square root 2, 1, 1. What happens if you apply it to state 1? You'll get a 1 because of this, but here there's a minus 1 times a 1, and this becomes a minus 1. So 1 over root 2, 1 minus 1. Now, if you think about the xy plane, what is the direction of this? If, say, this is the x coordinate, this is the y coordinate, what is the direction of this vector? Anybody? 1 over root 2 along x and 1 over root 2 along y. What's the angle? Hello?
Sir, it's 45 degrees.
Yeah, correct. And what about the bottom one?
Yeah, the participants are saying.
The bottom one? This is x, this is y.
Yeah, you can unmute yourself and can answer the question. So if you want to, the participants can unmute yourself and answer the question.
It will be minus 45 degrees.
Right.
In clockwise direction.
Yes. So what? Great. So 1, 0 is transforming this way. 0, 1 is transforming this way. So geometrically, what is happening? You started with 0 and 1. Let's see what happened to 0. 0 went 45 this way. But 1 went all the way down here. How do you represent this thing? What kind of transformation is this? Because normally, if you apply some matrix, which is unitary, it kind of represents a rotation, right? But this guy went that way and that guy went this way. How do you interpret this? This is like 135 degrees, but that guy went 45 degrees this way. So one way to see it is, think of this guy in between at 22.5 degrees. it's a reflection. 0 is getting reflected this way. And then you take the same guy at 22.5 degrees, and now 1 is getting reflected out here. So one interpretation is a reflection around pi by 8. And if you write the math for that, you'll see that it works out. The other possibility to look at it is so rotate 0 this way, right? Take it down here, and then by 45 degrees, and then reflect it along the x-axis. Boom, it goes there. 1, you rotate it by 45, come here, and then reflect it. It goes down there. So, and this can basically be a product of two matrices, right? One tried to do a rotation by this and then a reflection. Whereas the other one is a single matrix, which is a product of these two matrices. So you can have these interpretations of what's going on, but you can see what happened. 0, if you go back here, 0 went into this 45-degree state, which is a superposition of 0 and 1. And 1 also went into superposition, but with a negative direction along the 1 state and a positive direction along the 0 state. So this Hadamard gate, actually something very interesting. It took 0 to a superposition. It took 1 also to another superposition, which was different. So, and this kind of change is useful in quantum computations. We'll see very soon. Any questions here on the geometric interpretation?
No, sir. No question.
Okay. So there are other gates, like this is an identity gate. They can be, they're called polymatrices, which were, these kind of matrices came up in the physics domain. They were developed to study the spins of electron electromagnetic wave, things like that. But they are very useful in quantum computations. And if you do that physical transformation, and we have to rely on the physicists to actually do all of this, but as computer scientists, you will just know that these things are available to you to manipulate these qubits, right? And then you say, hey, I want to apply this gate, and you tell the quantum computer, do this transformation for me. And internally, it will do some physical processing to actually do the transformation for you. But you don't have to worry how it did, right? So it's all in the super cooled state, and the circuits function at very low temperatures and stuff.
Hello.
Yeah.
Hello, sir. I have a question.
Yeah.
Sir, the zero and that arrow mark and the 1 and the side arrow mark are they like two unit vectors? That is, we will represent the states in terms of those two unit vectors. Is it like that?
Yes. So think of this as this is a unit vector along x, and this is unit vector along y, right? And now, if you see what happened to 0, it went out here at 45 degrees. And then this guy, 1, went down here. But if you take this and this combined, where the new 0 is and where the new, where the new 0 is and where the new 1 is, if you put them together, they form a new basis. So actually, one is called plus and the other is called minus. So instead of, then you will say it's this vertical minus and greater than, and then vertical plus greater than. So you'll call this guy as plus, and let's say call this guy as minus, right? So you can have any basis you like, right? And then you will say what you're studying is in a superposition in that basis. So you can always do any rotation, right, in coordinate geometry, like that, and you have a new basis. So here also you can do any rotation, but the rotation is being facilitated by this Hadamard gate. So what what it's actually doing is taking you to a new basis, right? It's taking you, the sky is 45 degrees, the sky is minus 45 degrees. They're 90 degrees to each other, but in opposite directions now. 0 is leading 1, whereas 0 is lagging 1 in the anti-clockwise direction. Right? Here. Now 0 is gone at 45 degrees and 1 is gone here, but it's still another basis. So these two are now a new basis. And you can express all your computations in the new basis if you like. Or you can represent it still with the original basis and see what's happening. Does that answer the question? Yeah?
Yes, sir, I guess so.
Okay. Okay. So, and these are all polymatrics. This is like an inversion. Like if you take 0, 1 times 1, 0, and then 1, 0 times 1, 0, then if you apply this matrix on 1, 0, it becomes a 0, 1. And if you apply it on 0, 1, it becomes a 1, 0. So this is a NOT gate. And then there's another interesting gate called C0, which is like an exclusive OR, but it flips a target qubit if a control qubit is a 1. So let's say you're in a superposition, you have 2 qubits, right? One is a target, one is a control. You have there are 4 probabilities for M. So 0, 0, 0, 1, 1, 0, 1, 1. Let's say this guy is the control. If this guy is a 1, this guy is going to flip. So this state had a probability gamma 3. So you'll say gamma 3 times 1, 1. And the sky is gamma 4 times 1, 1. It becomes gamma 4 times 1, 0. So this physical transformation does this. It transforms, it flips the target qubit. Say this is the target qubit. 0 became 1 and 1 became 0 if this guy is a 1. But if this guy is a 0, there's no change to it. It's just like how an exclusive OR works. And it's actually useful in the Hadamard gate combined with the C0 gate lets you create entanglement. So I'll come to entanglement now. But was this clear? This what happened here? Any questions? Hopefully not. So quantum entanglement is like, you have this kind of a state, right? You have all of these 4 possibilities. But when you entangle, you only have maybe just this, and these guys go away. So, or you may have just these 2, and the other 2 are not there. It's like they're dependent on each other. If you have only 0, 0, and 1, 1, it means that they are equal. And if you only have 0, 1, and 1, 0, that means they're inversely entangled. If it's 0, 0, and 1, 1, they're directly entangled. Right? So if the only possible states are 0, 0, and 1, 1, if you measure any one of them, the other should be 0. If you measure any one of them, the other should be a 1. Right? So that's called entanglement. So now the funky thing is that it happens. It's a spooky action at a distance kind of thing, and they've done it with Chinese satellites, and have separated photons and taken them out to outer space, and then measured and on the satellite and then Earth, and they found the correlation. Right? So, and you can separate them by large distances, but you have to preserve this qubit. The moment you observe it, the entanglement is gone. So entanglement works only once. Like you bring these particles together, and maybe from you generate 2 things of opposite spin, and then you separate them apart. They're entangled. They're entangled until you observe any one of them. And then after that, if you do any processing on any one of them, it doesn't affect the other. So, but they'll remain untangled until you observe, right? But each photon electron is in a superposition of states until it is observed. and the observation leads to wave function collapse to one of the possible states. So this is kind of used in like quantum key distribution. For example, let's say we have 128 qubits, pairs of qubits, right? Separate them out. You and I have to, Deposhi and I have to exchange some encrypted message. What I do is I tap into my 128 qubits one after the other. And each one will come up with either 0 or 1, 0 or 1, 0 or 1, and so on. And then because we are entangled, the Deboshi's qubits, if they're directly entangled, will actually get all the same values. And then Deboshi can just observe, and he will just, because they've already collapsed because I measured it. And so magically, actually, the keys, a key got exchanged in virtually no time, right? So this is where it's kind of spooky action at a distance. But you don't know what it is going to be until you observe. So you can use it for this kind of key generation kind of thing, but you cannot send an email, for example, because that's a deterministic value. Because here you have to tap and observe and see what you get. But if I get a 0 on a qubit, Deboshi will get 0. So, and if I get a 1, he gets a 1. So this is something that's being used for quantum key distribution. So this quantum entangled state can be written as this gamma 1 0 0 plus gamma 2 1 1, where the sum of the squares of probabilities is 1.
Hello, sir.
Yeah.
Sir, can you move on to the previous slide?
Yes.
So, sir, in the last case, when when the wave functions collapse to one of the possible states, sir, is it random, or is there any specific states which it will collapse?
So, if you look at this, there's a probability associated with it being in 0 or it being in 1. So if 0 is more likely, then more often than not you might get this, and if 0 is less likely, then more often than not you'll get a 1. But you don't know. It depends on the probability associated with that state. But when you measure, you have a chance of either one, depending on the probabilities. And if they're equally likely, then it's 1 over square root for each one of them. Because the square of this is half. Half plus half is 1. The probabilities of the squares of the amplitudes.
Okay. And sir, another question is that Mr. Azad Ahmed is asking that, sir, has quantum entanglement been proven?
Yes. Actually, it's been demonstrated.
It's a practical case, right?
Yes. It has been practically demonstrated. And, they've taken qubits into space. They've actually just gone several kilometers away and then observed one. But you observe a whole bunch of them and make sure, that you're getting a correlation on the other side. So, if they were all, let's say all of them were equally likely, right? Then if I observed my 128 and I got a sequence of zeros and ones, and I know which was entangled with which with Deboshi's side, and if Deboshi observed, if he just gets random measurements, then there's no correlation, right, between them. But if he keeps getting, if I get a 0, if he also that particular entangled qubit also gets a 0, then you know that they're correct, and they have shown it. These are some things that are very hard to understand, but or even explain, but they do happen. Just like the double slit experiment or this entanglement. These are features of this quantum space, but we can actually exploit them if we know how it works. So that's why they're using it for key distribution and stuff.
Oh, thanks. Yeah.
So you notice that this thing 0001, you cannot decouple it in terms of just superposition of states for 0 and a superposition of states for 1, because you lost, say, 0 1 and 1 0 kind of thing. Otherwise, if you could separate them out, then each one is independent, and so there's no correlation. But here you can see that this thing is saying if one is 0, the other is 0. If one is 1, the other is 1. So they're basically entangled, and so if the state of any one of them is 0 or 1, the other also is identical to that, if it's directly entangled. Now, it can be inversely entangled also, in which case you have 0, 1, and then 1, 0. This is like, you try to generate two particles of opposite spin, and then they will have this opposite correlation. So if any one collapses to 0 or 1, the other one collapses to 1 or 0. But you know what kind of, whether it's direct or inversely entangled, and so you will know what to expect based on how you entangle them. And then it's not just two, so you can have multiple photons that you can entangle, and then you can have 4 directly entangled particles and things like that. And so how do you create entanglements? Sit through this a little bit, because once you go through this, you will know what happens inside the one. So let's apply, say, the Hadamard gate, right? What did the Hadamard gate do? What did it do to 0? 0 became transformed into superposition, right? Of 0 and 1. Right, because at 45 degrees, right? It's 1 over root 2 0 plus 1 over root 2 1. So this 0 became 1 over root 2 0, and this and also 1 over root 2 1. Right? See, remember this. Sorry. 0 became 1 over root 2 into 1 1, right? Which can be written as 1 over root 2 1 0 plus 1 over root 2 0 1. And then remember this one also. So, sorry. So you can see. So let's apply Hadamard to one of the qubits, and then look at C. So if you apply it on this 0, this 0 is spreading out. So the gamma 1 term, you see, is spreading out. Yeah.
Sir, I have a question. Sir, in case of this Hadamard thing, okay, sir, in this case where you have 0 0 0 1 1 0 1 1, we will have 4-dimensional system, right? In previously, when there was just 2 qubits, you had just one then that bracket, and then 0 bracket, and we had 2, say, like unit vectors. In this case, we will have 4 unit vectors, right?
Correct. So actually, this is a 2-qubit system. What you saw before was a single qubit system. Single qubit has 2 possible states, right? And it's in a superposition of those states of 0 and 1. Yeah. But it could be in a superposition of any basis, right? But the 0 is along, let's say, x-axis, and 1, let's say, is along y-axis. So what value you get in front of, say, shall I go back one second? Stop going. Just go back to show you this single qubit thing. This, right? So this is x-axis, this is basis, this is x direction, this is y direction. On a unit circle, where it would be will depend on these values, right? And the squares of these have to add up. So this is a single qubit. It's actually called a Hilbert space in C2, which is complex numbers. You need 2 complex numbers to actually. So, but it's just one qubit. It's in a superposition of 2 different directions, right? And with some probabilities, right, based on this. Okay. So let's come back here.
Yeah.
So these are 2 qubits. So when you have 2 qubits, we said 0 tensor product 0 is, and we wrote that as 1 0 0 0, right? That vector. This was 0, 1, 0, 0. This was 0, 0, 1, 0, and this was 0, 0, 1, 1. So it's a four-dimensional thing. These are four-dimensional column vectors. Think of each one of them as four-dimensional column vectors. So you're right, this is in 4 dimensions now. And there are probabilities associated with these. These are the amplitudes, the squares of the probabilities, right? So when you look at this, don't get scared. All you're seeing is just a column vector of dimension 4, right? And a weighted combination added up. But now the 0, actually write it as a linear combination of, because now when you apply Hadamard to this, apply Hadamard to this group of 2 qubits, but only apply it to one of the qubits. That's what you're saying. Apply Hadamard first to one qubit. So let's apply it to this guy. So that guy spreads out into 1 over root 2 0 and 1 over root 2 1 with the same amplitude. So it's gamma 1 by root 2 times 0 0. But this 0 0 also becomes a 0 1. So there's a gamma 1 by root 2. And then when you square this and add, you get gamma 1 squared. Right? Now look at this guy, 0 1. What is happening to 1? 1 was becoming 0 plus 45 and then a minus 45, right? So this gamma 2 became gamma 2 by root 2 and then minus gamma 2, 0 0 minus 0 1. Then you have what's happening here. Gamma 3 is 1 0. This guy is now transforming just like 0 0 happened. So this 0 is becoming 0 over root 2 and then 1 over root 2. And this 1 is becoming 0 over root 2 and then minus 1 over root 2. Okay, now you have this crazy thing here. The reason I kept, I could have kept like each one is half, 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 saying they're all equal, but then you wouldn't know what is cancelling with what. So we will make it equal now. But so because if it's half, 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 you get 1/4 plus 1/4 plus 1/4 plus 1/4. It's probabilities. So if they're all equal to half, then this was what we had before. But now pluses with things that have negative will cancel off. This 0 1 will cancel off with this 0 1 if gamma 1 equals gamma 2, and this 1 1 minus 1 1 will cancel off with this 1 1 because the minus sign, and then you're left with just 0 0 and 1 zeros. So, but there is 2 of them, right? And gamma 1 is half. So half 1 over root 2 0 0 and another half 1 over root 2 0 0. Again, half 1 over root 2 1 0 and half 1 over root 2 1 0. What happened to the other 0 1 1 1? They got cancelled out because these guys were all equal. Then when you add these things up, there are 2 of these, so this just becomes 1 over root 2 0 0 plus 1 over root 2 1 1. But entanglement, direct entanglement, we wanted a 1 here, right? Yeah. So we still have to flip this. And that's what the C naught gate does. So when you apply the C naught gate, you remember when I described the C naught gate, gamma 4 became gamma 3, gamma 3. So this thing, when the control bit is a 1, the target bit is flipped, right? That is a C naught gate. It's exclusive OR. So let me show you one more time. C naught gate. See here, gamma 3 1 0 became gamma 3 1, and gamma 4 1 0 became gamma 4 1. 1 1 became gamma 4 1 0. But this term is not there. This term is not there. We only left with these 2, and we put it through a C naught gate, so it takes it down to here. And now we have the entanglement state. Okay. So, but the quantum physicists create structures in their system. So you have to give a quantum instruction to your quantum processor, and it will kind of do these kinds of transformations. So we're almost done. About 10 minutes to go. So I'll try to explain what happens in quantum processing. So these kinds of transformations happen with different gates, concurrently exploring different possible states. The probabilities get refined. When you take a measurement, the state collapses to one of these possible states. And the higher probability state may be taken, especially if you're trying to minimize energy, then that state is likely to be selected. And you can have a hybrid system or an iterative system, like there's a famous algorithm called Shor's algorithm for integer factorization. So it is composed into two parts. The first part does some factoring on a classical computer, and the second part does some quantum Fourier transform inside a quantum processor, and you use the concurrent processing and all of that, and then take a machine, and then you're done. And then you could do it iteratively, like you could set something up, make a measurement, make some changes, send it back to the quantum computer, and so on. Now, there are two types of quantum computers. One are the circuit-based quantum computers, like these gates and all that I described. Then there are annealing-based quantum computers also, which is here, and D-Wave is the company that does that. And basically, they have a physical grid, with each qubit connected to some neighboring qubits. And then they try to do some processing. So there are some physical constraints on how many qubits can be connected to one qubits. So it's like a lattice of 2048. So you can see here this. Here the number of qubits are very small, but they are trying to do very exact processing. With this annealing thing, they're only trying to do some fast processing. So with some nearby computations. So it's a different kind of quantum computer. The qubits are locally interacting. The whole bunch of like 2048 qubits, chilled close to absolute zero. And if you want to do some optimization or research, you look for the lowest energy point in the landscape. And the quantum processor unit considers all the possibilities and determines the lowest energy and gives it back to you. So here is what it looks like, but it's basically like in a grid. Like if you look at the IBM thing, it's a huge thing, super cooled and things like that. So this is a quantum processing unit and operating at 20 millikelvin. There are two things like a quantum processing unit and quantum mechanical instruction. Just read through this. The QPU runs within the classical framework in the D-Wave, right, as if it's doing some computation. And but it has qubits and pairwise couplers for the local coupling between qubits. And this network of qubits and couplers is programmed with the quantum machine instruction. And then you try to observe an output of the spin values for these qubits. So here's an example, like a quadratic and constrained binary optimization called QBO. So you can have self loops, like when you're looking at an optimization problem, you can have weights associated with a single variable itself, and then products of those variables. So it becomes quadratic because there are product terms as well. And you're trying to minimize, something like x transpose x, qx. So this is a quadratic function. These are like constants, right? And then x transpose x becomes a quadratic minimization function. So here's a simulation that I did on my computer. So this is like a sample file. These values are self-coupled. 0 coupled with itself, 1 with itself, 2 with itself, 3 with itself. Notice 0 coupling with itself is 3.4. You're trying to minimize the energy. But if you try to add 0, then it will be a positive value. It will increase the energy. Same for 1, same for 2. But 3 actually reduces the energy. So it's a negative thing. So it's a good thing to add 3 into the system. So ideally, if you just look at it, you will say, I should have 0, 0, 0, 1 as my solution. But there are pairwise couples also, like for 4 choose 2, right, which is 6. The 6 couplings, 0, 1 is 2.2, 0, 2 is 3.4, 1, 2 is 4.5, 0, 3 is -2, and so on. So if you see, if you try to add 0, okay, 3.4, but let's say 0 coupled with 3 had a huge negative value, right? Then maybe there's a possibility to add 0. But no, this negative value is not that big. This guy is still dominating. Now, but if you look at 2 and 3, right? If you couple 2 and 3, that is a much bigger negative value compared to the self-couple on 2. So you'll say, hey, let's add 2 also. Let's make 2 a 1, because coupling with 3 actually makes it more negative energy function. So if you look at the solution, but then if you look at 1, that's the self-coupling is 4.5. If you try to combine 1 with 2, it's 4.5. 1 with 3, it's another 4.5. That's too much, right? So you really won't want to make this qubit a 1. This qubit also you will not make it to 1, because this guy is higher than, let's say, 0.3. So if you solve it, you'll find 4 bits. You get 0, 0, 1, 1. So 2 and 3 became 1, but 0 and 1 remained 0. And that is the solution. And you can walk through this example also. Similarly, I added one more qubit to this and similar arguments, but then you will end up with an assignment 10111 for the qubits. Okay. So essentially, what's happening is these qubits you have neighboring couplings that are set up, and then you try to do some optimization algorithm, but you cannot have everything connected to everything in this kind of computer. You can only have, so if you think of a graph, it has to be, the degree of the vertex should be small, so that you can connect it up to a few other vertices and stuff like that. And then the weights on the edges becomes these couplings that we have, right? And then you try to send it to the quantum computer and ask it to minimize the energy. Out it comes with the value. So yeah, this is an example D wave. So it does some approximate calculations, but useful for energy optimizations. So yeah, there are some references here, and I've sent the slides to Deborshi. These things you can take a look. So any questions? You've run over time quite a bit.
Yeah. Thank you, sir. Yeah, there are a few questions. Yes, Mr. Gaurav Chaudhary is asking, it's a very good question that, sir, are Google and IBM Q computers more general quantum computers? And also, what are your comments on the Google quantum supremacy? IBM said it's not perfect.
Yeah, so I guess, no, I think we should let IBM and Google fight it out. But yeah, they are actually, these are more general computers. You're right. This, as you noticed, this guy cannot do all kinds of computations. Only some nearby, sparse graph related, like map coloring kind of algorithms you can run. But this kind of computer, you can, with all these gates and all of that, you can connect any qubit to another qubit. So like for the Shor's algorithm, you'll have at the inputs, you'll have some Hadamard gates, and then it will go into some quantum Fourier transform and things like that block. So you can actually build a proper computer with these kinds of bits. And so they are limited in their size. This is large because it only allows some local connections.
Sir, the D-Wave computer is like non-programmable, and the IBM one is like programmable. Is it like that? I'm not an expert in it. I'm just trying to draw an analogy. That is.
No. Actually, it is programmable. So there's this quantum machine instruction that you send to it. You set it up. Like, you said this test.cubo file, right? You're saying all these coefficient values, those become the weights of the coupling between the qubits and things like that. Then you say, hey, go find the values of the qubits, for example, 0011, right? That minimizes the energy of the system. The energy of the system is given by, the coupling values, right? Times the values of the qubits. So if that's why I was saying, if 0 coupled with 3, then this value is still smaller compared to the negative value that you have on 0. So it's not helping you to make 0 or 1, right? So 0 bit qubit just remained at 0 whereas qubit 3. So that's what you do. You set up the computer with the quantum machine instruction, and it finds you the lowest minimum state of the qubits. that has the minimum energy.
Mm-hmm.
And in this case, it's a different setup. There are different values, and then you get a different solution. So you're at the mercy of the computer. It will find. But the thing is, hopefully, like it's exploring many different possibilities because of superposition to quickly find an answer.
Okay. So, sir, another thing, sir, in generally I'm asking, in future, there will be jobs in quantum computing. So, sir, what should we learn and how should we prepare so that we can, get, because it is a very futuristic thing. And the way everybody is going on is, I think, quantum computers will become very much used all over the world. So, how should we prepare? Because it is so much different from conventional computer science or electronics and anything like that. So that's what I was asking.
Right. So all these guys. So D-Wave, unfortunately. Hello. Yeah.
Hello, sir. Sir, I'm asking. Sir, please answer, sir.
Yes, sir. Yes, they are here.
Okay. So this list, right, we have here. So all these guys have put their stuff on the web. Intel recently actually released a library along with its an optimized library for its implementation to simulate, quantum computers. So a lot of things you actually don't need to have access. You can probably just simulate and see if your algorithm is doing a good job and things like that. IBM has made its quantum computer available in the cloud. Google also has made its quantum. All these guys have put their actual quantum computers in the cloud. And for students and researchers, I think they give a lot of free time on the quantum computer. So you should just sign up if you for these things. You just go to the websites and the cloud platforms. Now, D-Wave is a little more secretive. I think it is restricting the usage of its actual quantum computer to, I think, right now, US and Europe. But its simulator is still available. Like what I did here is actually just ran the simulator. I just built it and ran it on the computer. So I didn't actually send it to the actual one. But you can still see how it's working and things like that.
Okay.
So at least you will know how to program these computers if you use their simulators that are available. And once you're ready, you can actually try to run some of the real stuff on these things with the free time that they give you. So.
Okay.
So Google them, and you'll find that they'll definitely give you some free time.
Yeah. There are lots of questions are there. So my request to participants is that you can unmute yourself and directly ask the question to sir. So that will give more clarity rather writing your question. So one by one, if you can kindly unmute yourself and ask the question, it will be easier. Okay, sir. By the meantime, like another question I am asked, I'm just reading it out. So Mr. Vincent is asking that does it mean that by using the quantum entanglement, there will be zero error when transmitting the signal at any possible environment?
Yes, I think to a large extent you can say that, because if the entanglement works fine. I think though when they test it, a large fraction of the qubits were found to be correlated. So, but if it was not correlated, then you would have had random assignments, right, to those qubit values. So, but some qubits are found to be in error, maybe because there was some problem with the entanglement itself when it was physically done. But a large number of bits. So then what you can do is, if you know that there will be a small errors, then you can use error coding kind of thing, so you can still recover from it, maybe even if you have some errors in the values. But there are some qubits could be in error. So, but it's more of a function of the physical process. Maybe there was something went wrong in the entanglement. And as they may refine these things, hopefully they won't have any errors. The other thing is, even the quantum computations, they're not perfect. So some qubits are more reliable than others and things like that. And nowadays they're designing quantum compilers which will try to identify which qubits are more reliable than others and then assign computation to those qubits and things like that. So I think we're looking at some of these things because the quantum computers are not perfect in everything that they do. But the thing is, anyway, you're working with mostly with probabilities, and hopefully, uh, a few errors here and there will not affect the overall computation, and it will still proceed fine in terms of averaging effects and stuff like that. Right now, these quantum techniques are not 100% perfect.
So another question, like by Mr. Arnav Bag, is like, are there analogous developments for superconducting qubits that are used in a universal quantum computer? This may be particularly useful in applications like quantum digital signatures, where we need to store the states for a more extended period.
Right. I mean, but you have to store it, in that superposition state, and then take a measurement later. But definitely possible. But it's very expensive, right? Because these things have to be kept in that cool state and not touched at all. So you better be sure that you're not wasting those qubits for a long time and just holding them there. So.
Sir, one thing I want to ask, sir. You said that there is something called quantum key distribution via satellites. That is being experimented now. Okay, that is, they are sending some. In the previous one of the slides, actually, so you said, sir. Can we just disrupt that quantum key distribution process by someone sending random photons, okay, towards the same detectors, and just create a lot of noise, and that just disrupt the communication? Because
you mean like where the qubits are, so you kind of disturb the system. That's possible. Yeah, that's a different kind of attack, a physical attack. Yeah, but hopefully, the people who are holding the qubits are keeping them close to heart, so you can't tamper with them. So. Yeah, there are a lot of variations on this key distribution protocols, and it's likely that key distribution might be one of the earlier realizations in the communication space and networking space. Yeah. But also, like a lot of our, let's say we do some resource optimization in a wireless network and things like that, or some traveling salesman problem. All these optimization problems can benefit from quantum computing.
Yeah, so I think this will be the last question I'm taking, and that might be the question for many of the participants. That, sir, regarding the future of the quantum computing or quantum computation in 5G, and the job scopes and research scopes, like issues in the future. So, sir, I think if you can address this.
So there can be two possibilities. I think we can have some. I was saying, hey, a lot of software is getting implemented in microservices. I think we can have, in the near term, we could have quantum-inspired algorithms just running on classical computers, on a very fast classical computer. But maybe it still does better with its, concurrent search, with treating the information in a superposition state kind of thing, mimicking the behavior of quantum. But maybe in the future you may still have a microservice that will actually go interact with an actual quantum computer and come back with an answer. So that hybrid kind of model, right? So when we have this, both are possible. This thing initially you might have just everything happening here, but it's maybe quantum inspired on the left on the classical processor. But if we have a quantum processor available, we can actually do a hybrid system together. Both are possible. And think of this still microservices running, interacting with a quantum computer, while other things are going on, this 5G infrastructure and so on. So, yeah. But definitely a lot of, it's a very a rich area for research. If you're looking for new problems and stuff like that, and you can try to put some quantum framework around it and try to solve it and come up with a PhD thesis. And you should enjoy the process of doing your research. Don't worry about the job, because as part of this, maybe you will learn how optimization theory. You will learn optimization theory, you will learn matrices, and basically you'll learn how to use some cloud platform and computing. And you will be an expert in many different things, but you will have rich scope to do your research as well. So, and then when you come out, maybe the world is still not ready, or maybe it is ready. We don't know, but yeah, it's up to you. Maybe you come up with something that readies the world as well. But I think it can be a fun area, and to kind of look at problems differently and think differently. So please do give it a try. And some of these books are good if you take a look. And this book is especially good from a CS perspective, right? These two are more physics-related stuff. You guys were a little scared about it, but you can use it as a reference. And I think there are Indian editions for all for these. This you can get online, I think, in the electronic version. So yeah, get hold of this book, Nielsen and Schwab, if you want to take the CS part of it forward. So, but, also maybe follow some lectures online to learn and things like that.
Yeah, I think that's all the question answer session, and we already exceeded a lot of time. And I know that this kind of interesting topics is very difficult to discuss within 1 hour. So first of all, yeah, I think no more questions are there. So first of all, IEEE Computer Society Student Branch Chapter IIT Kharagpur really thank to Dilip sir for his valuable time. He's very busy and getting time for us. We are really thankful to him. And we have from our IEEE Kharagpur section, we have a small token of appreciation for you, sir. Because everything is online now, so the thing will be dispersed by a post to you after the lockdown will be over and the situation will be under control. And we really thank to all the participants also for their patience and participating. And I hope in future also we'll meet in this kind of sessions. And yeah, I think that's all from my side. So
thank you, Devarshi. Yeah. Thanks to everybody for taking the time.
And the slides that you can share with the participants. And
yeah, you can share them. Yeah.
Yeah. Again, sir, thank you.
Oh, actually, I think I made a couple of edits. So don't send it yet. Let me while we are presenting. Right, I found a couple of typos. So let me send you the updated version, and then.
Okay, sure, sir. Sure. You once you send me the updated version, and then I'll forward the same among the participants.
Okay.
Yeah. Thank you, sir.
Thank you.
Thank you all. Yeah.
Bye.
Thank you, sir. Yeah. Bye, sir. Yeah.
Bye.